Hi all, I am Amarendra Reddy, registration number 23MIA1012, and in this video presentation we are going to explore how quantum computing is transforming the field of cryptography from classical encryption methods to the urgent need for quantum safe solutions. We'll break down the key concepts and algorithms that define the future of the secure communication. Before we dive into the details, here's a quick look at what we'll be covering in this presentation. We start with a look at modern cryptography and the concept of store now decrypt later. Next, we'll understand symmetric cryptography, what it is and where it is used, followed by asymmetric cryptography, including RSA and ECC. Then I'll explain how RSA works, both in theory and with a practical example involving two people communicating secretly. After that, we'll move into quantum computing, what it is and why it's a game changer for cryptography. We'll cover quantum attacks using Shor's and Grover's algorithms and see why they pose a serious threat. Then we'll look at several post-quantum algorithms that are designed to resist those threats. These include Crystal's Kyber for key exchange, Crystal's Dilithium and Falcon for digital signatures, and Sphinx Plus, which is based on secure hash functions. Finally, we'll wrap up with a conclusion on how we can move forward towards a quantum secure future. Let's begin now. In today's world, attackers don't always need to crack encryption on the spot. Instead, they can save encrypted data now and simply wait until computers become stronger. This is called store now, decrypt later. The danger is that when quantum computers arrive, they will be able to break today's encryption quickly. That means things like bank records, medical files, or even private emails we send today could be exposed years from now. So the lesson is clear. We need to move to quantum safe encryption early, not after it's too late. That's why cryptography has to constantly evolve. What is secure today may be insecure tomorrow. Understanding this life cycle is key to why we study not just current algorithms but also the future ones. In symmetric cryptography, we have a single shared key for both encryption and decryption. Because of this, we have to share the key with the decryptor before we share the data. It's fast and resource efficient but might not be that secure. That's why we go for asymmetric cryptography. We'll look into symmetric cryptography more in the next slide. Symmetric cryptography uses just one secret key for both locking and unlocking the data, which is why it's used in VPNs, Wi-Fi's, and decryption algorithms. Algorithms like AES, DES, and SACHA20 are common examples. The big problem though is sharing the secret key. If someone intercepts it, everything falls apart. So while symmetric systems are powerful, they can't solve the key exchange problem on their own. Like if someone intercepts the key here, they can decrypt the ciphertext and get to know the plain text. That's why symmetric encryption, though fast, is not preferred for more sensitive information. Unlike asymmetric cryptography, in asymmetric cryptography, there are two keys. One for encryption, which is a public key. Anyone can see it, anyone can use it, anyone can encrypt any data with using the key. And one for decryption. Only the person who has a private key for decryption can decrypt it. No one else can decrypt it. No one can access the private key. That's why asymmetric cryptography is mostly preferred for more sensitive data. We'll look at its working in the next slide. Asymmetric cryptography fixes the key sharing problem in symmetric cryptography by using two different keys, a public key and a private key. You can share your public key openly and anyone can use it to encrypt a message for you, but only your private key can decrypt. This is the basic idea behind RSA and ECC. These systems are slower than symmetric ones, but they are essential for things like secure websites, digital signatures, and cryptocurrencies. Without asymmetric cryptography, we couldn't have secure communication on the internet. As we can see here, we have two different keys. One, a public key which anyone can access to encrypt the plain text, and we'll get a ciphertext from that. But only the people who have the secret key can decrypt it. Even if you have public key and you don't have secret key, you can't decrypt the message, but you can encrypt it. This is the this is the magic of modular arithmetic. RSA is probably the most famous asymmetric algorithm. It starts by picking two prime numbers p and q. Then we multiply them to get n, which will become the part of public key. The difficulty of factoring n back into p and q is what makes RSA secure. Then we'll pick up a public exponent, usually 65537, to calculate private exponent called d. Why 65537? Because it's neither too small for the attackers to brute force the algorithm, nor too big for the encryptors to make it hard for encryption. Now, the public key is e comma n, and the private key is d comma n. The encryption is raising the message to the power of e mod n, and decryption is raising the ciphertext to the power of d mod n. Only the private key makes the math work. That's why it's more secure than symmetric algorithms. Let's break it down with two people, Alice and Bob. Step 1, Key generation. Alice chooses two large prime numbers, P1 and Q1, to form N1. Bob does the same to get P2, to use P2 and Q2 to get N2. Each person chooses a public exponent, E, and computes psi of N of their respective N's. The public exponent D might be 65537 or some other number. Then they will calculate their private key D. For communication, if Alice wants to send a message to Bob, she encrypts it using Bob's public key, which is E comma N2, and only Bob can decrypt it using his private key, which is D comma N2. And if Bob wants to send a message to Alice, she will use E comma N1 to encrypt the message, and Alice uses D comma N1 to decrypt it. In this way, if we intercept this, we can only see the numbers E and N which they share, N1 or E comma N2, which they share to each other so that they can encrypt it. But using this, we don't know what D is, so we can't decrypt their messages. We can only see the encrypted messages. That's why RSA is more secure than symmetric algorithms. Quantum computers work in a very different way compared to normal computers. Regular computers use either 0 or 1 the bits to represent data, while quantum computers use qubits, which can simultaneously be 0 and 1 at the same time. That's called superposition. Qubits are also linked through entanglement, which means changing one instantly affects the other. Because of these features, quantum computers can possess many possibilities in parallel processing. That makes them extremely powerful for certain problems, like factoring big, factoring big numbers, searching databases, which is why there is such a threat to cryptography. Like in RSA, the whole point of encryption and decryption, the whole point of security in RSA is that the numbers are too large to factor them using a normal computer. But if quantum computers come in, they can factor them in like way less time, making it harder to encrypt, making it harder to secure a data. One of the biggest threats from quantum computing is Shor's algorithm. It's a method that can factor large numbers very quickly on a quantum computer. And since RSA and ECC rely on factoring being hard, Shor's algorithm could break them completely. On a normal computer, factoring a 2048-bit number would take millions of years. On a quantum computer running Shor's, it would be done in days or even hours. That means once big enough quantum computers exist, our current public key systems won't be secure anymore. Rover's algorithm is a quantum search algorithm which is used in an unsorted database to find a specific item. Normally, we have classical encryption algorithms which we use to find an item in an unsorted database. But for that, it takes O of n time. But Rovers reduces it by almost root n times, which is a massive speed if you consider the data to be very huge. This impacts symmetric cryptography like AES and hash functions. Normally, for example, a 128-bit AES key would take 2 power 128 tries to brute force, which is impossible with classical computers. Grover's algorithm reduces that to about 2 power 64 tries, which still is huge, but it's much easier with a quantum computer. The fix is simple: use a longer key. So AES 256, for example, will still be secure because even with Grovers, it offers about 128-bit strength, which is strong enough for current world. But why the urgency? Quantum computers are too far in the future. The urgency is because these quantum threats are not just theory. Researchers and governments are already warning about them. Attackers could be recording encrypted data traffic today, waiting to decrypt it once quantum computers are ready. That's why we can't wait until quantum computers arrive. Moving to quantum safe systems takes time, and if we delay, years of sensitive information could already be at risk. That's why the push for post quantum cryptography is happening right now, while quantum computers aren't even ready. As you can see, quantum computing is already advancing rapidly. There are large scale machines are practical yet. The threat is already real because there are people analyzing and saving the data for later to decrypt it. Sensitive data sent today could be stored, that is saved today, decrypted later. Classical systems like RSA, ECC, and some symmetric ciphers are vulnerable to attacks like shorts and globals. We urgently need to adapt to quantum resistant algorithms. Global efforts include NIST standardization aim to build future-proof encryption so that even quantum computers can't decrypt them. This protects communications infrastructure and national security in quantum era. Crystal's Kyber is one of the leading post-quantum algorithms. It's designed for secure key exchange like RSA, but here it replaces the factoring. Instead of using factoring, we use lattice problems, which are harder for quantum computers to solve. Kyber is fast, it's efficient, and safe even against quantum computers. NIS, NIST has already chosen it as a standard for post-quantum cryptography. So in the future, when you connect to a secure website or a VPN, it's very possible that Kyber will be the algorithm protecting your communication. Crystals DD3 is another post-quantum algorithm, but it's used for digital signatures instead of key exchange. Just like RSA can be used to sign data, dilithium creates signatures that are secure even in quantum world. Signatures are super important because they prove software updates are real, certificates are valid, and data hasn't been tampered with. If RSA proof signatures get broken, the whole trust model of the internet fails. Lithium is designed to prevent that in a quantum world. It's also based on lattice cryptography. It's digital signature, so it's designed for signing and verifying messages instead of in place of key exchange like RSA. It is built to be efficient, compact, secure. It is expected to replace RSA. It is selected by NIST as a standard for post-quantum signatures. It's, it ensures authenticity of like software updates, certificates, or data, so that it hasn't been tampered or it's illegal or something. Falcon stands for Fast Fourier Lattice-based compact signatures. It's known for being lightweight and efficient. It's perfect for devices with limited processing power. Like dilithium, it's also lattice-based and resistant to quantum threats, making it ideal for secure digital signatures in the quantum era. Its advantage is that the signatures it generates are smaller and faster than dilithium's, which makes it great for devices with low limited power or memory, like IoT gadgets and smart cards. The downside is that it's harder to implement currently, but it's still one of the top candidates for post-quantum use. Most likely, Falcon and dilithium will be used side by side, depending on the needs of the system. Spins Plus is a different approach. It's hash based instead of lattice based. It doesn't rely on problems like factoring or lattices, but instead uses secure hash functions to create signatures. This makes it extremely robust and secure even if other mathematical assumptions fail. It's stateless, reliable, and another strong option in post quantum cryptography. But the only problem is that its signature size is too large when compared to dilithium or alpha. But it offers strong resistance against both classical and quantum attacks. So it is also one of the top contenders for post-quantum cryptography. In conclusion, quantum, quantum computing is going to change cryptography completely. RSA and ECC won't survive once large quantum computers exist, and even symmetric systems like AES are affected. But the good news is post-quantum algorithms like Kyber, Dilithium, Falcon, and Spins are ready to take over. The main point is that we need to prepare early. If we start adopting to these new algorithms now, our digital world can stay secure even in the quantum era. Thank you for watching.